Hello everyone. Welcome to my channel. Today we're doing a deep dive into Drake, a powerful robotics simulation framework from MIT. I'll walk you through every single line of a complete Drake system called DoubleSystem that doubles its input. By the end, you'll understand exactly how Drake systems work at the code level. Let's start at the very top with the imports. Imports LeafSystem. This is the base class for all basic systems in Drake. Think of it like a building block. Imports BasicVector. This is Drake's way of representing vectors of numbers. Imports context. This is crucial. The context holds all the system's state, inputs, and parameters at a specific time. Imports DiagramBuilder. This is how we connect multiple systems together. Imports simulator. This runs our system forward in time. Imports numpy as np. We use this for mathematical operations. Class DoubleSystem. Defines our class DoubleSystem that inherits from LeafSystem. Inheritance means our class gets all the capabilities of a LeafSystem. Definite defines the init method, the constructor that runs when we create a new DoubleSystem. Calls super init. This calls the parent class constructor, initializing the LeafSystem part of our class. Self declare vector input port declares an input port. Declare vector input port is a Drake method that creates an input port. The first argument u is the name of the port. The second argument 1 means it accepts a vector of size 1, a single number. Think of this like declaring, this system has one input called u that takes one number. Line 42 declares an output port. Declare vector output port creates an output port. Y is the port name. 1 means it outputs a vector of size 1. Self CalcY is crucial. It's the method that will be called whenever someone asks for the output value. This is our computation function. Line 44 defines our CalcY method. This is where the actual computation happens. Context. The first parameter is the context. This contains all the current system information. Inputs, time, state. Output, BasicVector. The second parameter is where we put our result. None. This method doesn't return a value directly. Instead, it modifies the output parameter. Line 55 gets the input value. U equals self.getInputPort gets the first input port. Eval evaluates the input port at the current context. This reads whatever value is connected to this input. The result U is a numpy array, even though it only has one element. Line 59 does the actual computation. U0 gets the first element from the input array. We multiply by 2 to double it. This is where y equals to u happens. Line 62 puts our result into the output. SetFromVector is a BasicVector method that sets its value. We pass as a list. Even though it's one number, Drake expects vectors as lists or arrays. Line 65 defines a test function. Line 69 prints a header. Line 72 creates an instance of our system. System equal DoubleSystem. Line 75 creates a context equal system. Create default context. This gives us a workspace for our system. Line 78 sets input value to 5.0. Line 79 fixes the input value. Fix value sets the input port to always return 5.0. Line 80 evaluates the output port. Eval calls our CalcY method and returns the result. Line 81 prints the result with an F string. Line 82 uses assert to verify the result equals 10.0 within a small tolerance. If not, the program stops with an error. Lines 84 to 89 test with negative input minus 3.0. Same pattern, set input, evaluate output, check result. Line 108 defines another demonstration function. Line 115 creates a DiagramBuilder. This is how we build complex systems from simpler ones. Line 118 adds our DoubleSystem to the diagram using Builder. Add system. Line 124 builds the diagram. This finalizes the connections. Line 125 creates a simulator for our diagram. Line 126 gets the mutable context from the simulator. This is where we can change values. Line 129 gets the subsystem context. This is important. Each system in a diagram has its own context within the larger diagram context. Diagram.getMutableSubsystemContext gets the context for our specific DoubleSystem within the larger diagram. Line 133 sets the input to 7.5 in the subsystem context. Line 136 evaluates the output, which should be 15.0. Lines 155 to 161 create a sine wave source class. This shows how to create a time-varying input. Line 159 declares an output port because this system generates values. Line 164 gets the current time from the context, context.getTime. Line 165 calculates a sine wave, amplitude times sine of frequency times time. Line 166 sets the output. Lines 176 to 177 connect the sine wave output to the DoubleSystem input. This is how we build complex systems. Lines 179 to 181 add a logger to record our output over time. Vector log sync is a system that records data. Line 182 connects the DoubleSystem output to the logger input. Line 190 runs the simulation for 10 seconds. The simulator calls our CalcY method many times as time advances. Lines 246 to 247. This is the standard Python pattern. When we run this file directly, it calls the main function. Now let's run that code and see what happens. I'll explain every single output that appears on the screen and what it tells us about our system. First, we see this header, DoubleSystem demonstration, followed by a line of equals signs. Then, system equation, y equals 2 by u, and where u equals input, y equals output. This confirms what our system does. It's a simple mathematical relationship. Output y equals 2 times input u. The equals signs create a visual separator. Think of it as a title card for our demonstration. Next we see testing DoubleSystem . This starts our testing phase. We're going to verify that our system works correctly with different types of numbers. Here's what happened in test 1. We gave the system an input of 5.0. The system calculated the output as 10.0. The expected 10.0 shows what we mathematically expect. 2 times 5.0 equals 10.0. The numbers match perfectly. Now we test with a negative number in test 2, negative 3.0. The system outputs negative 6.0. Expected? 2 times negative 3.0 equals negative 6.0. Correct. Test 3. Testing with 0. Input 0.0 gives output 0.0. 2 times 0 equals 0. Perfect. Test 4. Testing with a decimal, 2.5. Output is 5.0. 2 times 2.5 equals 5.0. Correct. Finally, all tests passed. That check mark is important. It means every single test worked correctly. Our system handles positive numbers, negative numbers, 0 and decimals, all correctly. Now we see demonstrating DoubleSystem in diagram . This is a different test. We're putting our DoubleSystem inside a Drake diagram. That's a network of connected systems. Input, 7.5, output, 15.0. We give it 7.5, it outputs 15.0. 2 times 7.5 equals 15.0. Good. Verification. 7.5 times 2 equals 15.0. This line just confirms the math manually. Then we see information about the system's ports. Input port U available at DoubleSystem.getInput port 0. Output port Y available at DoubleSystem.getOutput port 0. This is technical but important. It shows that our system has properly defined connection points. Other systems can connect to port 0 for input and port 0 for output. This means our system can be part of larger, more complex systems. Now the really interesting part. Advanced example. Time varying input . We're no longer testing with constant numbers. We're feeding our system a sine wave, a signal that changes over time. Simulated 2 time steps. This might seem strange. Only 2 time steps? That's because our systems have no internal state that needs frequent updating. Drake, being efficient, only calculates at the start and end. Final time, 10.00 seconds. We simulated for 10 seconds. Final output, minus 2.1761. Expected, minus 2.1761, 2 times amplitude times the sine of frequency times t. This is the most important result. Let me explain what happened. We connected a sine wave generator to our DoubleSystem. The sine wave formula is amplitude times sine of frequency times time. Our sine wave had amplitude 2.0 and frequency 1.0. So at time t equals 10 seconds. Sine 1.0 times 10.0 equals sine 10.0 approximately equals minus 0.54402. Input u equals 2.0 times minus 0.54402 is equal to minus 1.08804. Through DoubleSystem, y equals 2 times minus 1.08804 is equal to minus 2.1761. And look, the actual output minus 2.1761 matches exactly what we expected minus 2.1761. This proves something crucial. Our DoubleSystem doesn't just work with constant numbers. It works with signals that change over time. This is essential for real-world applications like audio processing, control systems, or any system where inputs aren't constant. The sine wave test shows our system correctly processes dynamic signals. At every moment in time, the output is exactly twice the input, even as that input changes continuously. So what have we demonstrated? 1. Mathematical correctness. The system always computes y equals 2 times u. 2. Numerical robustness, works with all number types. 3. Framework compatibility, works within Drake's system architecture. 4. Dynamic capability, handles time-varying signals. 5. Connectivity, can be connected to other systems. If you enjoyed this walkthrough of actual simulation results, hit that like button and subscribe for more hands-on robotics and simulation content. The code is in the description if you want to run it yourself. Thanks for watching, and see you in the next video.